Too many buttons to have to press. Okay. So last week we talked about the normal distribution, and that seems weird, and how we can use it to calculate the areas under curves for a single value. In this week, what we're going to be looking at is the let me get the whiteboard. So last week we talked about, I like this better. Maybe not. What? Z was equal to x minus mu over sigma. And I said, don't get used to it because we're going to change it this week. And what we're changing it to is, this is for when x is one value. And this is for when the number of x's is more than one. Okay, so really what we're doing is we're finding the average of all our values and then dividing them by the square root of n. But when x is 1 here, the average of one thing is just that thing. And the square root of n is 1. When n is 1 is 1. So this comes out to be this. This is only true when the number of x's is 1. So we really were using this all along. It's just that they didn't tell you that, and they don't tell you that right away. And the reason they don't tell you that right away is because you have to understand, A, first how to use it, and then B, that this works for any kind of distribution as long as it's continuous. And because what we're doing is we're taking the averages, and then the averages will always be normally distributed. I was talking about the Museum of Science in Boston. They used to have this Plinko game, basically, in the math area, and they would just drop balls, and no matter how often they dropped the balls, it always came out normally distributed. You know, there'd always be a bunch in the middle, and then there'd be fewer on the outsides, and you could, every time you would just hit the button, it would bring the balls back up and drop them again, and they would just, no matter where they started, they would all just randomly kind of fall to that outside. And so you are always getting that. And if we took the average of those things over and over again, we would find that that value comes in the middle, and then we would have a normal distribution. It kind of works like when we're talking about, and the other thing that they talk about in this is that since the averages are normally distributed, the sums of those things are normally distributed, just because they have to be. Because if we add up a whole bunch of things and we get these averages, adding them all and dividing by n, so if we are getting the averages being normally distributed, that means the sums must have been as well. And we can understand that because we all know when we roll two dice, right, we get something that looks like this. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. The graph looks like this, where 7 is the most common value, and then 2s and 12s are the least common values. And if we were to take the average of these things, it would come out to be, we get the half values, and it would just be shorter. The numbers would be smaller, but the graph would still be the same. And so that's what happens as we roll these things, as these things happen. And the more dice we rolled, the more normal this would even become. So normal distributions can actually happen in discrete values, because once we roll these up and sum them, we can take the averages and find out we would get values that aren't discrete anymore, and therefore we would have more of a continuous thing. So if I were to roll 100 dice, and sum them up, and then do this, I would still get this. I would get a more normal curve as I went along, and the points would start. The bars would start to disappear and be more of a graph like that. And that's what happens. That's why we do this. Where is my central limit theorem? Leave it in the center. Of course not. I must have taken it out at some point. All right, I gotta remember to put it back in. So here, where did that thing go? Must be in this page. There it is. I always have to download this thing. I should just make a video of it. That way I don't have to download it ever again. And it's locked, so you can't make the changes. So Trump is not on this list. But it's the heights of all the presidents up to Obama, because they were all there at the time. And I'm just waiting for it to open. I don't need this open that many times. I just want it once. Love waiting for things. So anybody enjoying the rain?
It's cold.
That's better. It's cold and rainy outside. I don't like it. That's fine. I get it. I locked it at some point, so nobody could change it. And of course, now I don't remember the password. Yeah, I'll probably put them up. Oh yeah, that's Aaron, and then I'll put them in Blackboard afterwards. But yeah, they are in Cengage automatically once you do this. So here's all the president's heights. Okay, and then what this does is it takes a sample of 9 of them. 3, 6, 9, yes. And I have a few of them. 1, 2, 3, 4, 5 of them. And so what's going to happen is every time I can't enable editing because it won't. Every time I hit F9, it changes the value. Okay, and so what happens here is we have this is the population mean and the population standard deviation. So this is the average height of all the presidents is 179.8 centimeters with a standard deviation of 6.8 centimeters. Now, what this does is this picks a random height. I don't know why it's not picking a random number, but and finding the z-score and finding the probability of getting that one thing. So these are all the values that could have happened. Now this is what it's doing is it's pulling out the 9 presidents. So president 30, 32, and sometimes they do get counted more than once. That's perfectly fine because it's just random. Right? We're randomly sampling them. We're getting their heights. We're finding the means of those samples. Okay, and finding the standard deviations of those samples. And so this is the z-scores of both of those things. But what really we're interested in is this over here. And as you notice, these two values, I can't even highlight it, so it stays pretty close to this 179.8. Right? And the more times we do it, the more samples I have, this would actually stay at 179.8. Okay, this would, the average mean of the means would be the population mean. And then if we were to take the standard deviations of those standard deviations, because there's 9 of these things, would be a third of this number. So about 2.3, which is about what happens every time. It goes in and out, but we get to around, we're always around 2.3, or not too far in one way or the other. And so that's what happens with these standard deviations, is that this curve becomes normal, but not only that, it becomes very skinny. All right. So this thing here has, I should have probably graphed it out, but it has no shape. It's just a whole bunch. It would be a histogram of a whole bunch of ups and downs. Whereas if we were to take the graph of these things and continue on, if I did this millions of times, it would have a, and I would end up graphing these, I would have a normal distribution. I would have a curve, and with a mean that's the same as this value, and a standard deviation that is 1/3 of this because I had 9 of them. If I took 100 things, it would be 1/10 of those. So as we take more samples, the standard deviation gets smaller and smaller because we're taking the square root of n. So if this was 100 things, we would divide this by 10. If we had 144 things, we divide it by 12. I'm just trying to pick up perfect squares. If we had 625 things, we divide this by 25. So as our sample gets bigger, our standard deviation gets smaller and smaller and could eventually become 0. We would have no standard deviation. The thing would, the averages of the averages would be that, would be the mean all the way through, always. So that's why we don't take infinite numbers of them, but add in it would cost too much. But it allows us to show how we can turn any distribution into a normal distribution. So when they do that, they talk about in the first problem, an exponential distribution, which we didn't discuss. So an exponential distribution, really all we're trying to find is the probability of getting one thing, and then the probability of if we had 25 people. So what would be the difference of those things occurring? And we only have to care about the average one, but the homework problem has all the rest of those, so I'm going to do them. But an exponential distribution if I were to do this, it's exponentially distributed. So the exponential distribution is in the form of 1 over m. Thank you. So we have to care about this thing called m. And m is just 1 over the mean. So this is the mean. So m would be 1 over that value. Okay. One over m. Oh, that's a 0.10. That's why. Oh, I bet I know what it is. I probably have a stop plot on. I do. That's why it's not working. And that was right in the first place. All right, let me. Zoom. This window here, so I negative. Okay, that's why. All right. Something's wrong here. Hold on, let me bring it back up just because I know that looks wrong. continuous random variables, the exponential distribution. Go away. Yep. Oh, I forgot the x. That's why. I knew something was missing. I just couldn't figure out what. X. That's better. Okay, I knew something was wrong and I just couldn't figure out what it was. I was forgetting the x part. So here I'm going to start this as -1. I'll go to 10 and 2, 1. Let's go from 0 to, oh, I don't know, 2. Graph. Yeah, that's better. Okay, no, when you have to go, go, because like those things are far more important than this. So I'm sorry, but definitely go to that. Right. So what we have is here is this is what our exponential graph would look like. All right, and we're going to find the area under the curve from a certain space. Okay, and so here they want to know what is x. X is just amount of change that a single student has. Whereas, and then they're going to ask what is distribution. Well, this is exponential, so just exp. And then you can just write this in as 1 divided by 0.72. I'll just have the fraction bar, the number logs on. 1 divided by 0.72. Because it's just 1 over whatever the mean is. They don't, this here is all cleaned up for you. But this is far more useful because we're going to be talking about money as we go along. So you're better off. That way you don't have to think about it. It's just 1 over whatever they tell you the mean is. And it accepts it as an answer, right? So it doesn't have to be cleaned up at all. And then what is x bar, which is really the thing we care about. And x bar is just the average. If we did this over and over and over again, picking 25 people, what is the mean? The mean is still going to be the same thing. All right. And then the standard deviation is going to be the standard deviation divided by the square root of 25. Well, the standard deviation of an exponential distribution is the mean. So this number would be for both of these, but what they did is they have to divide this by the square root of 25. So we have 0.72 divided by the square root of 25, and that's where they get this number from. Okay, so this exponential distribution will become normal over time, with the mean still being the same thing and the standard deviation just being divided by the square root of whatever the sample size is. Make sense? Okay, great. Somebody likes it. Then they ask us, well, what is the probability of finding a single person who has between 78 cents and 94 cents if the average is 72 cents? And there's a formula to calculate that, and it is for the exponential one. We're not going to need this after this, so it's e to the negative over m minus e to the negative a over m, where a is the lower value and b is the upper value. And so it's subtract those, you'll get your area. All right, so in my case, we have 0.79, 0.78, and 0.94. So to do this in the calculator, it's second ln negative 0.94 divided by 0.72. And then I use this over arrow to get out of the exponent. So those of you with the older calculators, I'll show you how to do it as well. You're going to use the parentheses, and then you don't have to use that over key because it just gets out of it. Minus second ln negative 0.78 divided by 0.72. Oops, I mixed them around. Sorry. I've had A minus B. I have them in the wrong order. A minus B, where A is the smaller one and B is the larger one. So, mess this up. But I know it's not right because I get a negative space. So that's how I can easily fix that. So again, if you have the older one, it's still going to be second ln, and you're going to get a parenthesis up here, right? E, you're going to have the negative, this number 0.78 divided by 0.72, and then you're just going to close the parenthesis, and it will stop being in that space. Minus, and then again the E, and you'll have the parenthesis, negative 0.94 divided by 0.72. And then when you enter, you'll get your area under the curve. And so what this says is that 6% of the people are in this range. About 6.5, almost 7% of the people are in that range. And then they want you to graph it. And again, they only have 2 that have between. But to figure out which one it is, we have to figure out where does it cross the y-axis. And so that we can just figure out what is 1 divided by 0.72. And we find that it's about 1.4.
Professor.
Yes, ma'am.
Why are you putting the negative sign in front of the 78?
Oh, well, because the formula to do the math, we have to get the negative of those things. So there's no way to put the negative in the middle, so it's really kind of negative over there and the negative b, because we're going to have 1 over m, and that these graphs are going to be negative. So whenever you're graphing it, m to the negative 1 over m.
When I type it in, I get the error quit go to.
X. So you're hitting the minus. You're hitting the minus sign. You want to use the negative sign. Is that one?
Use minus sign?
Or use the negative sign, the one in the parentheses, not the minus sign. So second negative, and then I have the 0.78 divided by the 0.72, and then get out of it so I can subtract. And then brings me back up there. Negative. So you're going to subtract one of them. You might have put the negative there as well.
No, I added a parentheses. I see what I did wrong. I put a parentheses around it.
There's all kinds of little things that can easily go wrong. You know, you can type one, if you open a parenthesis and you did. I'm assuming I forgot a decimal point somewhere. Oh, I forgot the positive. I forgot the negative there. These are negative. Yeah. So yeah. So you can if you have a closed parenthesis, it doesn't. Then you need an open one. It would do that. It's all kinds of little things that could go wrong. But so yeah. So this is our graph, and we want to make sure that we are putting in the values correctly. So it's negative m to the x, but m is 1 over the mean, so that's why I always. Those are the things you use, but this is the only place we have to do this. This is the only time you're going to have this question. So even if you skipped it, you're like, I don't get it, that's fine, because it really isn't about this one. It's about this one, but I like it because it shows how the graphs are different. And we can see that, okay, this is an exponential curve, and this is, when we take the means, we get a normal curve. Right? So the reason we like normal distribution, we like taking the averages, is because we can take, once we do this, we get a normal distribution, and we can just use the z distribution. So we want to find the normal CDF where my lower bound is 0.78, my upper bound is 0.94, my mean is 0.72, 74, 72. And my standard deviation was the standard deviation divided by the square root of n. Now, if you didn't do this calculation already, then we could just type it in as 0.72, 72 divided by the second square root of 25. So we could actually have it calculate that for us. And just puts it in there. So those of you with the old calculators can just type it in just like this, where you have your normal CDF parenthesis, you know, your lower bound, your upper bound, your mean, and your standard deviation. Well, the standard deviation you can actually type in like this, and when I hit enter, I'm going to get an area. And it is 27.2. So 27% of the time, we're going to get the average of 25 students between these two numbers. Whereas when we picked a single value, we only got it 7% of the time. So the reason that happens is because when it's normally distributed, we have that curve, and then we have a smaller standard deviation of that happening. So the spread is smaller as well. So because this goes on forever, whereas this, while it kind of goes on forever, it really kind of stops after 4 standard deviations. The probability of those things happening becomes almost 0. So we can find the areas of this stuff much easier. And this math is simple. We just go to our calculator and we have a formula for it. We have a button for it. This one we had to type in a formula, know the formula, type in the formula, calculate the things. This we don't even have to know what this is really, you're really doing calculus here. But the computer does all the calculus for you. It's finding the area under a curve, which is what calculus is. And we don't even know what this curve is. We don't have to know what the formula for this curve is. We just know it's normally distributed, and it will calculate the area under that curve for us. So then we can easily find, well, which ones are between, well, these two, and then which ones have that space and the mean of 72. So this one has that space, but the mean is like 90. This one has that space, but the mean is 72. That's why it's this over that one. And so we like, and then the question asks us, well, why is there a difference between these two things? And the reason is because one is normally distributed and the other one isn't. You know, and it makes life a lot easier. We're taking the averages. The averages are always going to be normal, and it, as long as it's continuous, and actually as long as it's any distribution, it will. If we keep taking the averages, we will of a bunch of poles, we will get a normal distribution that includes binomials and Poisson, all the other things. We can actually use the normal distribution to calculate those on large numbers of tries, because we're going to take, especially if we're taking average things. So
could you possibly go back to part E? Because I'll be honest, with all those very lost.
well,
there.
that's what. So the easiest suggestion is you can skip it. But yeah, so because it's not on the test, it's not something that I want you to know. I want you to know this one. I want you to know F. We're not like like I said, the only reason I like this problem is because it shows how like most statistics classes take a normal distribution and then take the averages of it. And so you have a normal curve and then you have a skinnier normal curve. And it's like, well, okay, well, why do I care? But when you find out that any curve becomes normal is kind of an important factor. That's what the whole central limit theorem is about. But no book I've ever used, except for this one, explains or demonstrates that. So to get this, again, all we have to do, so we do second ln, right? Then we have to put the negative in because these are all always going to be negative. This is our first number, so 0.78, divided by our mean, which is, we get out of the exponent, right button, and then we're going to subtract the other one. So e to the negative 0.94 divided by 0.72. When we hit enter, we get our space. The big thing is that we can see that there's a giant difference, that this had only 7% of the time in this area, whereas this one has 25% of the time is in that area. Sorry, this area.
Okay, that makes much more sense. I was wondering why we were dividing by 0.72.
Yeah, so yeah, this is just, it's just a formula where it's mx, where, so this is the x, the m is 1 over the mean, so that's why it's easier to do the division this way than it is to like write out and figure out, well, what is m here? M is 1 divided by 0.72, and they turn it into this fraction here, which is but it's just easier to not deal with that because it's not a clean decimal at all. You know, it's a repeating decimal, so you have a fraction times points, you have a fraction times a decimal, and it's like, well, why would I want to do that kind of weird work? I have a decimal here and I have a decimal here, why can't I just use those? So that's what I do. It's just easier knowing, thinking it's 1 over the mean. And if I multiply this times this, I get 0.78 over 0.72. And if I multiply this by this, I get 0.94 over 0.72. So it's just easier and cleaner and works much better in your calculator, whereas we're going to do all the math than dealing with this fraction and this decimal.
Right.
So it's just ugly. It's an ugly thing, and it, like I said, this is the only time you're going to do it unless you take algebra 2. because that's when they get into or physics or calculus, because that's where you get into E's. You know, after like this is the like we don't discuss E in anything. It's not important to us, like in statistics, really. It's just that knowing that it's a continuous distribution is really the only interesting thing of it for statistics. So that's the only reason it's included in the book, because she knew that she was going to use it later on in chapter 7. So it's in chapter 5 if you really want to go back and look at it, and then it's in chapter 7 again. The other one eventually will come up is the uniform distribution, which also is a weird formula. Again, you're not ever going to need that. Except that I like it for showing how the central limit theorem works so much better. So, and yeah, it's just weird formulas. That's really all it is. So here they talk about farms in 1940, and that the average size farm was 174 acres, and it had a standard deviation of 58. And we have no idea if that's normal or what kind of distribution that is. It could be uniform, it could be anything. But it tells us what the standard deviation is. And we're going to randomly select a bunch of farms. So X is just the size of a single farm, where X bar is the average of 41 farms. And that's going to be the big difference between these two things. Because if I'm finding the probability that a farm is less than 150 acres, a single farm, I need to know these things here, and I will use the normal distribution. Well, actually, I don't even know what distribution I would use. That's the problem. But if I know that I'm looking at the average size of 41 farms, what's the probability that that's less than 150 acres? I can use the normal distribution in that. So because I have no idea what kind of distribution this is, I would never be able to figure out what's the probability of finding a single farm at any size, or a single farm less than a size or bigger than a size. I wouldn't be able to find any of that information because I have no idea what this distribution looks like. But when I find out that we do averages, I know I can use the normal distribution. And so the normal distribution, the X bar follows the normal distribution with this mean and this standard deviation divided by the square root of this number. So this is going to be 58 divided by the square root of 41. And that's where they get that value, rounded to 2 decimal places. And then just you continue to use this number then afterwards, because there'll be rounding errors built into this. And so all your answers will have rounding errors. So it's just one of those strange things that happens. And so here they want to know, what is the interquartile range? So that means the lower 25% and the upper 25. So 25% of the values are less than what, and 75% of the values are less than what. And so we go to our distributions. And because we know the area of the curves, we're going to use inverse normal. And my first area is 25. And my mean is 174. And my standard deviation is 9.06. And I find that it's 187.889, so that rounds to that. And then I do the same thing with the next one. But like I said, this calculator is great because I can bring back a previous problem. I don't have to do any extra work. I just change this to a 7 because it's the upper quartile. So first quartile is 25th percent, the third quartile is 75th percent. So again, I hit enter, and it gives me those. So 50% of the houses of the 50% of the farms are between 167.89 acres and 180.11 acres on average. If I was to take an average of 41 houses, sorry, 41 farms, not houses, because that'd be a really big house. So the average size of 41 farms is between these two numbers. 50%, the middle 50% are between those two numbers, those two acreages. And that's why it's far more useful than knowing a single piece, because like I said, I would never have any idea how to calculate this because they don't tell me what kind of distribution it is. Even if I knew what kind of distribution it was, I still might not know how to do it. But we can at least look that up. But if we know nothing about it, just like the presidents, I don't know the distribution of what the presidents look like. I know the numbers, but I don't have a shape for it. It doesn't have a shape because it's a whole bunch of disconnected things, and it's only 44 of them. So and the reason there's 44 is 44 presidents. Like, you know, some people had more than one term. So one president had 2 separate terms, which is kind of strange. So he comes back as a sequel later on. And so because there's no real distribution of this, like I really wouldn't be able to, you know, get the interquartile range in the middle 50%. Well, yes, I could look this up, but it's not normally distributed, so I really can't use those values. It doesn't mean anything. You know, I could put them in, I guess, in line in order, and then, you know, find the quartiles that way. But it's still kind of a weird thing because it doesn't really have it doesn't really have a distribution, whereas this does. And I could very easily find my quartiles in this, and it would make sense. So if I was taking the average of the heights of 9 presidents, I'm always going to get, you know, here's my mean, here's my standard deviation. I can find that out. Which of the following is not true? Well, the area in the curve is always 1. The mean, median, mode are equal. So because they're equal, they're not skewed. It just kind of like you can't have this and this be true. So while I'm really bad at drawing the normal curve, sometimes I get lucky. Not too bad. The mean, median, mode are the same value. So there's no skew here. Skewing would be that or that, and I don't know which one is skewed to the right. I think this one is. So this can't occur because here's where the mean, you know, here's the mean, here's the median, here's the mode, here's the mode, here's the median, here's the mean. So those things can't be true when you have a skewed graph. Mean, median, mode are always the same when it's symmetrical. I'll just fly through these. Here they just want you to calculate what the standard deviation is, so I'm not even gonna, what it's gonna be a normal curve with a mean and a standard deviation. I'll let you work on that one. And it's 4 questions, 4 choices, so not really gonna worry about it. Here, cost of unleaded gas in the Bay Area once followed an unknown distribution with a mean of $4.59. I kind of took from this problem here. And a standard deviation of 10 cents. So they then sample 16 gas stations. And they want to know what is the probability of finding the average of 16 gas stations with a price over $4.69. So we have a normal I'm going to do that. Ish. Was it 459? 459, okay. And they want to know what's the probability of finding 16 gas stations that have an average price over $4.69. which doesn't sound like it would be that hard, except that you're taking the average of 16 gas stations, and the standard deviation, remember, it's going to now be the standard deviation over n. It's going to be 0.10 divided by the square root of 16. Okay, which comes out to 0.025. So that means that this here is 0.025. That's 4 standard deviations above the mean. 1, 2, 3. So 4. So we're looking at stuff that's 4 standard deviations above the mean. So the probability of that happening is very small, because the probability of getting more than 3 standard deviations is only 0.015, 1.015, 1.5%. So 4 standard deviations is tiny, right? And so without me even doing anything, I know it's not that, and I know it's not this. So it's either unknown or it's almost 0, and I could find out exactly what it is. I can come here and I can say, all right, well, second vars, I have a normal distribution, normal CDF. I'm going from 469 up to infinity, 1 second e, so second comma, 99, where the mean is 459. And the standard deviation is 0.10 divided by 4, because I'm not going to bother writing it because I mess it up. But I can know that I don't have to worry about. I know the standard deviation of 16 is 4. So I get this. And here I'm going to change the mode. Instead of it being float, I'm going to have decimal place. Now do it again. No. All right, I'll do 6 decimal places. And I don't want scientific. No, well, that wasn't helpful. All right, never mind. Trying to get rid of the floating decimal point, and it didn't seem to want to work. So those force it to have spaces. All right. Okay, so I have to move this decimal point 5 places to the left, so I get 0.000003, which is pretty close to 0. I mean, it's a lot less than that, and it's not unknown, so that's why the thing it's almost 0. If I was to turn this into a percent times 100, I get 0.003% chance of that happening. So we have a tiny percentage chance of finding 16 gas stations that have an average price over $4.69. So you got to remember, this book was written when gas was high. Okay, this book was written in the early 2000s when gas prices were above $4 a gallon. All right, which is why you don't see Hummers anymore. We like the Hummer, but the Hummer only got like 8 miles to the gallon, so which was great in the 90s. People loved it, but then gas got really expensive, and they realized, and it had like a 30-gallon tank, so you're spending over $100 to fill your gas tank. people didn't particularly care for that, so they stopped buying them, which meant that they stopped selling, and which meant that they stopped making them. So that's what happens when things are no longer viable. That's why until gas is over like $8 a gallon, there will always be gas cars. Because even when they were $4 a gallon, that's when the hybrid came out and people started to buy them because they're like, oh, well, I can get 50 miles to the gallon. It's not going to cost me as much. But then they realized that I can't fit anything in it. So they were like, well, so they'd have a hybrid and an SUV. So they really weren't, because when they had to take the kids to soccer or hockey or football, and they needed, room for 6 kids and luggage, they realized that they couldn't fit it into a hybrid because, you cannot fit very much into a Prius, let's be honest. And then they came so then they're like, oh, well, we need to be green, this whole green thing, which is great. We have global warming. Stop eating my mic. So again, they came out with electric cars, which I don't quite understand because they're still run off of coal. So they hate coal because it's bad for the environment, yet that's what electricity comes from most of the time in your house. So you're fueling the coal industry, which is getting more efficient and cleaner, but still it's less efficient and less clean than gasoline. So I don't understand the whole point of that. I mean, I guess if you have solar power on your house and you have an electric car, then it's not costing you anything. But electricity is expensive in the Northeast. That's why we don't have electric heated houses, because it gets too cold and it costs way too much money. And those people who have it really, 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 really get disappointed about it. So we were looking at a house when we were first buying houses, and we're like, oh, it has electric heat. It's beautiful. It has everything we want, except it has electric heat. Let's get out of here. Can I please have my computer back? Okay, go sit over there. I love you, but you're being a pain. All right. So number 6 here asks about if we have a normal curve and a central limit theorem, if we take the averages, what do the curves look like? Now, when I was first doing statistics, we would always draw it like this, but we never put numbers in. So I would always go, well, this is the answer. This is what X bar looks like, and this is what X looks like, and I would keep getting it wrong, and I'd be like, well, why am I getting it wrong? And then I realized that it was because it had numbers in it, and I wasn't thinking about the numbers and what they meant. And so what they mean is that because X has a standard deviation of 13, right, that this here is only one standard deviation. We're only seeing one standard deviation of the graph. But we're seeing all of the standard deviations of X bar. So that's why it's this answer and not this answer, which is what I usually think of. Like if there were no numbers in it, would have been the right graph. But because there's numbers in it, it has meaning, and therefore I have to look to see what's being shown. And so that's where this is the right graph. So what is the distribution of X bar? Well, it's just n, because it's normally distributed, has the same mean, and then it's the standard deviation divided by the square root of n. So however you want to write that is perfectly fine. If you want to write it, so 13 divided by 5, it seems weird that they write it as a fraction and not as a decimal, where it's 2.6. That's what I would have written, because I know 5 goes into everything nicely. But they wrote it as a fraction. I don't know. You could have written it as 13 divided by the square root of 5, except that we don't have a square root sign. So there's no way to do that. But if we did that, and you didn't know what it was, so 13 divided by the square root of 5, square root of 25, you get the 2.6. I would put that in there. I don't know why they write it as a fraction. It just seems weird to me. They say sketch the graph, okay, but they don't ask you to do anything with the graph. And then we're finding the probability that it's less than 60. So let's clear the graph, clear the page. We have a graph. The mean is 60. The mean is 60, and this is normal. How much is on this side?
$40.
Nope, the mean is 60. What percent of the data is below 60? Remember,
50%.
50%.
59.
Right, because this is the mean, median. So half the data is over here. That's 50%.
Oh,
They ask you a silly question. Like, they're like, well, what percent of the data is less than that? Well, the mean is 50, the median is 50, so it's 50. You don't have to do any work for this question. It just seems like a silly question, but they're asking you kind of, do you understand what mean, median, and mode are? What is the 40th percentile? Well, so that will come into our graph. And because this is, we know the area, we're going to do inverse norm. Where the area is 40%. So remember 0.40, not 40. If you type in 40, it doesn't understand it. It'll tell you have an error. The mean is 60. And the standard deviation was 2.6. 13/5. And they give us our value. Right. So because they're asking about the percentiles, that's the area under the curve. If they'd said 40, what number, 40% of the values are greater than what, then you would have had to do with 60%. It would have been the 60th percentile. But because they're asking the 40th percentile, we don't have to do any extra thinking. Here they're asking what is the, again, sketch the graph, what shade the region, label the scale. Don't do anything with that picture when you're done. And then how much of the data is between these two decimal places, between these two numbers. So again, we're going to go to normal CDF. We have our lower bound, our upper bound, our mean, and our standard deviation. We graph it and we find that that's the amount of area between the curves. Same thing here. What is the area between the? Then they ask us about the sums of the numbers. Well, so if the average of 25 things is 60, so remember, to get the average, that's the sum of the x's divided by n. Well, if I know the average and I know n, so I know this was 60, and this was 25, I can find this by just multiplying these two numbers together. So 60 times 25 is going to give me what the sum was. And remember, these sums will be normally distributed. Get 1500. Now, then they give you this way to find this out. All right. So it's going to be they're going to tell you it's the standard deviation times the square root of n. So the reason that's true is because here we found that the standard deviation was the standard deviation divided by the square root of n. So we multiplied this by n, we have to multiply this by n. Well, if I have the square root, if I have n divided by the square root of n, I get n. So n divided by the square root of n, I get the square root of n. So we can either take this thing here and multiply it by n, because if we don't know, we're only given this thing, we're like, oh, I got to multiply that by 25. Or if we know what this was, we can multiply this by the square root of n, and that would give us this value. So either way will work. Because 2.6 times 25, 2.6 times 25, 65, or 13 times the square root of 25, 65. So either one of those will give you the same answer. And so it doesn't matter which way you get it, but what happened was they took the things that were in this distribution and multiplied everything here by 25. So the standard, the average times 25 gave us the square root of n, the sum of the x's. The average times 25 gave us the sum of the x's. The standard deviation divided by the square root of 25 gave us the standard deviation times the square root of 25. So either one of those cases will be fine. You can do it in either way. Because I thought there was a one. Oh, okay. I was going to say that's one about the length of books, but it is that one. All right. So then they ask you, what is the upper quartile for these? So they want to know the 75th percentile for this distribution. And they want to know the area between two numbers for this distribution. So I'm going to let you guys do those on your own. But that's, because remember, this is going to be inverse normal, and this is normal CDF. The last one, again, is a different distribution. They're telling us that it's a uniform distribution, which means it makes a rectangle. Okay, and the area under this rectangle is 1. Okay, where the height is the probability. This is the lower bound. This is the upper bound. All right, and the average, the mean, is A plus B over 2. All right, the weird one is the standard deviation. So this is the mean. The standard deviation is the square root of b squared minus a squared over 12. And I don't know why any of those things are there. Okay, I've never seen a proof for it. I just take their word for it. It's in the book. I'm going to accept it as that's what it is, because somebody has figured it out at some point in time. So this is the standard deviation of this, of a uniform distribution, always. And so what we have to do is calculate that for this thing. So what does x mean and what does x bar mean? What is the distribution? They're uniform, so they use a u. The lower bound, upper bound. So they're telling you 10 and 25. What is the mean? Well, that's just these two things added together divided by 2. What is the standard deviation? So it's 5 squared minus 10 squared divided by 12. I get that, and then I take the square root of it. That doesn't come out to be 4. Oh, hold on. The square root of 25 squared minus 10 squared is that divided by 12. That's not right either. Hold on. What? Go back to the book. I'm doing something wrong. Oh, okay. That's what I had wrong. I had where it was squaring in the wrong spot. I knew there was squaring and subtraction. I just had them doing it the wrong thing. So subtract the 2, square it, and then divide by 12. I knew something was wrong, but I couldn't figure out what. So 25 minus 10, we square that, divide by 12, and then we take the square root of that. So second square root, second answer gives us the 4.33. Or if I were to do this all in one thing, second square root, second square root, parentheses, 25 minus 10, close parentheses, squared, divided by 12. So I like just doing it out in steps. That's just me. You can see where I did something wrong, like taking the squaring them both first. I knew that was something was wrong, but I couldn't figure out what. So subtract them, square the difference, divide by 12, take the square root. It's kind of long, but again, it'll be easier than finding the area under a single thing. You have to find the area of the rectangle. And so the area, the height is 1 over the difference of those two things. So, and then you would multiply by that, you get a rectangle, and then you go from there. But this again, we just use the mean and standard deviations. And then you're going to take this and divide by the square root of n to get x bar. So it's going to be still the same mean. And then you're going to take this standard deviation and divide by the square root of n. And in this case, n is 55. So that's how they get this space. Everybody understand how I got this now and this? Because that's where people tend to get lost on those two things, especially when I mess it up. The lower and upper bounds respectively, yes.
Yeah, Professor.
Okay. So especially when I mess it up the first time and the second time and the third time, something goes wrong. I'm like, I've messed you up. And so you're just going to use this formula here, find the standard deviation, and then you're going to take that and divide by the square root of n. Just this thing, I believe there's probably one. So you'll need to be able to do this. just like there may be one exponential one, but you have to remember that the standard deviation is the same as the mean, and then you just take the square, that over the square root of n. So you won't be doing the uniform part, but you would be doing the central the means of the central limit theorem part of that. So you'll be doing this part. You'll be doing. You might be dealing with the sum of the x's. And so here they want to know, well, what's the mean and standard deviation of the sums of the x's, and then what is the areas of the curves below or between or above something. Okay. I figured that's what you said, but I figured I'd just go back and check just to make sure. So these here, again, you're going to take the mean because it's the sums. You're going to take this 17.5 and multiply it by 55. You take this number and multiply it by 55. You get the values. Then they want to know, do you think it's unlikely for a professor to read more than 1,040 pages? And the answer, of course, even if it was likely, the answer is no, it's unlikely, because that's a lot of reading for a final, which has to be in a couple of days after grades are due. Like after the final is done, grades have to be in fairly quickly. Even if it's a week, you have to read 1,000 pages, grade them, probably not going to happen. And then they want to know, well, why? And so you calculate the probability of getting that thing. And it's 0.0097, so less than 1% chance of that occurring. And why is it also unlikely the average length of pages will be less than 12? Well, again, because the means are 17 and the standard deviation is 0.5, so 17.5 and 0.5, so 3 deviations away would be 16 pages. You might find a single paper that's 12 pages long, but the average length of them won't be, because that's 5.5 times by point. So 11 standard deviations away from the mean, not very likely to occur. Like really, 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 really unlikely to occur. And you could look it up and find out exactly how unlikely it is to occur. Second distribution. Nugget, stop. That's just so destructive. So from negative infinity up to 12, where the mean is 17.5 and the standard deviation is 0.584. It's 0. Right? The probability of that happening is 0 because it's 11 standard deviations below the mean. So there's no chance of that, virtually no chance of that occurring. It's a number preceded by over 99 zeros. So the chance of it occurring is negligible, is minuscule at best. It's the probability of having 2 cats behave for an entire day. And so that's why those things are unlikely. And like I said, the reason you can skip this thing here, right here, this part here, and not a big deal. Remember, if you get an 85 or better in homework, it's an A. So if you skip a few problems, there's going to be some where they tell you to upload the graph. And I have no idea if those get corrected or not if you upload a picture, because I don't look at it. And I doubt the computer looks at it. So maybe it just looks at it and says, okay, you did it. And Mark gives you a correct point. I don't know. So I don't worry about it. If you get above an 85, it's an A. If you get between a 70 and 85, it's a B. And if you get below a 70, it's an F. So, and homework. So if you skip and you're like, I missed how that one was done, I can't figure it out, don't do it. It's not gonna be it's one problem out of like 1,000 or two, so it's not worth your effort. You're still gonna have a 90 something to look at. And what I really look at is not necessarily, I mean, I look at the grades, but this thing also tells me how much time people have spent. And so I can look and go, all right, well, this person isn't going to get anything, and this person might have a low amount, but this person has 400 minutes already, and we're into week 7. Like the average, like I get this person has 1,300 minutes. I have people who have spent 3,000 minutes doing homework in this class. 2,000 and 3,000 minutes isn't unusual. So I'm not worried. Like that's where things pop up. Like if you spent 150 minutes, you're probably not getting the work done. So I'm going to stop recording.